Hi everyone. Today we're going to be working on problem D from Educational CodeForces Round 147, black cells. The problem is you are playing with a really long strip consisting of 10 to the power of 18 white cells, numbered left to right as 0, 1, 2, and so on. You're controlling a special pointer that is initially in cell 0. Also, you have a shift button you can press and hold. In one move, you can do one of three actions. The first action is move the pointer to the right from cell X to X plus 1. Second move is press and hold the shift button. Or the third move is release the shift button. The moment you release shift, all cells that were visited while shift was pressed are colored in black. Of course, you can't press shift if you already hold it, and you can't release it if you haven't pressed it. And our goal is to cover K cells, but there's a restriction. And in each segment, Li to Ri are the only segments we can color. And we have to find the minimum number of moves we can make in order to color at least K cells black. So the form of the input is a number of test cases, with each test case containing a value of n and k, n being the number of segments and k being the desired number of black cells. And each of the segments is given by a start point Li and an endpoint Ri. It's important to note that each of these segments are disjoint of each other, i.e. Li is less than or equal to Ri, which is less than Li plus 1 minus 1. Let's work on solving an algorithm for the problem. So we know we have exactly k cells that we need to color. And let's say that our last cell is in some range Li to Ri and is cell number y. Now consider the number of moves we use. The number of moves we use to go to the y cell is the y moves that consist of adding 1 and the number of shifts we click and release. And the number of shifts we click and release is 2 times I. Recall that I is the number of ranges that we've clicked, and we need 2 moves per range to select certain numbers of cells. Now we've dealt with the first time we can end our sequence, but how can we reduce this? Consider some range Lj to Rj. When is it better to move this to the end rather than clicking shift on Lj and releasing on Rj? This is the same as considering the question, when going to y plus rj minus lj plus 1 is better than, in fact, just dealing with rj and lj and clicking shift on this range. Let's just consider the moves to y plus rj minus lj plus 1. In this case, the number of ranges we cover is 2 times r minus 1 instead of covering r ranges, but instead we have to move to y plus rj minus lj plus 1. And when is this better than just moving to y and using r ranges? The number of moves to just y using r ranges is 2 times r plus y. Just doing some math, we can see that this first quantity, 2 times r minus 1, plus y plus rj minus lj plus 1, is less than 2r plus y only when rj is equal to lj, or we are only dealing with one cell. This yields the following algorithm. Our first step is to find the first spot where we can end. Then, once we find the first spot where we can end, we'll deal with all the ones and tack on as many ones to the end of our current segment as we can. And as we can see from before, the only way we can improve from our current state is if we have a 1 we can tack on to the end. And we'll do as many of this as we can. Start by implementing this problem. So first we have to deal with a number of test cases. Let's call this number of test cases t. We'll input into this number of test cases t, and we just have to iterate through this t. And now within each test case, we're dealing with an integer n, the number of segments, and an integer k, the total number of squares we need colored. And let's just input into these two numbers. And our next 2 lines of input are a list of the start points and a list of the end points. So let's create a vector for the starts and a vector for the ends. Now we'll input into these two. And we'll input into our ith range. And we'll do the same for our rith range. Next, what we're going to do is we're going to attempt to deal with the actual problem. In the actual problem, what we want to do is we want to keep track of a current number of colored squares. We want to keep track of a number of ones used. Sorry, let's keep these all as long longs because in the problem we're given that they could be long longs. And our answer, let's keep track of an answer. And what we're going to do is we're going to iterate through segments and see which one's the most optimal. So we want to keep this as a very large value. So let's keep this at 2 times 10 to the 18th. And at this point, we'll keep a Boolean variable of whether or not we're done. And from now on, we just have to iterate through. And at each step, we're going to see our current length of our segment. And this is just going to be the right endpoint minus the left endpoint plus 1. And from here, we can see that if we are done only when our current length of segments sums to a number greater than or equal to k. So if our colored plus our current length is greater than or equal to k, we're done. So we'll mark our done as true. And at this point, we want to calculate our current answer. So to calculate the number of ones moved, we can do this by calculating the minimum of the number of ones and whatever is left in the current segment. And that's the current colored plus our current length minus the k that is used. And on the right side, or our right endpoint, what we're going to have is we're going to have some integer that's equal to a value, our left endpoint, plus the number of squares we need to color, minus the ones that are already colored. So basically, we're adding how many more we need to color to our left endpoint. And then we're going to add the number of ones we can move. And we'll subtract 1 because our right endpoint is included in our count. And our current cost is just going to be a max of our left endpoint and our right endpoint, our furthest right endpoint, plus 2 times the number of ranges used. And that's just I plus 1 minus the number of ones we've moved because we've gotten rid of those ranges. And then our nth is the minimum of the current answer and the current cost. And now, regardless of whether or not it's satisfied, what we want to do is we want to change our colored squares and add the number that is in the current length. And if our current length is 1, then we'll add 1 to our number of ones used. And now, after our loop, if we are done, then we want to output our answer. Otherwise, we want to output something that's just -1 because we cannot get enough squares colored. And let's see whether or not this code works with the input given in the problem. And as we can see, our code works on the input given in the problem. Let's see whether or not it works on our CodeForces. And let's submit it to CodeForces. And it's currently running, and as you can see, it was accepted. There's our code.